A mysterious force is tearing our universe apart at an accelerating rate. This is the enigma of dark energy, an invisible presence that dictates the ultimate fate of everything we see. For centuries, we were certain that gravity would slowly pull the cosmos back together. But 2 decades ago, a shocking discovery revealed the opposite is true. By the end of this journey, you will understand not only how we uncovered this cosmic secret, but what it means for the final destiny of all existence. We will explore why the universe is speeding up and confront the possibility that everything from galaxies to atoms could one day be ripped to shreds. What do you believe is the ultimate fate of our cosmos? The first clue that our universe was not static came from a man peering through a giant telescope on a California mountaintop. Edwin Hubble made a startling discovery in the 1920s. He found that galaxies are not stationary islands in space. They are all racing away from us and from each other. The cosmos itself was stretching, growing larger. This was the first evidence of a universe born from a colossal explosion, the Big Bang. To understand how fast this expansion was happening, astronomers needed a way to measure both the distance to galaxies and their speed. They found a key tool in the light these galaxies emit. When a galaxy moves away from us, its light waves get stretched out, much like the siren of an ambulance drops in pitch as it speeds away. This stretching of light towards the red end of the spectrum, called redshift, became a cosmic speedometer. By measuring how red a galaxy's light appeared, scientists could calculate its velocity. But knowing how fast a galaxy is moving is only half the story. You also need to know how far away it is to understand the true rate of the universe's expansion. This is where one of the universe's most brilliant and violent events comes into play, a specific kind of stellar explosion known as a Type 1, a supernova. These are the deaths of dense stellar remnants called white dwarfs. They always explode with nearly the same intrinsic brightness, a known and predictable amount of light. This makes them perfect standard candles. Think of a street lamp. If you know how bright it truly is, you can tell how far away it is just by how dim it appears from your vantage point. Astronomers use these supernovae in exactly the same way across the vast emptiness of space. For years, teams of scientists meticulously searched the skies, waiting for these brilliant flashes to appear in distant galaxies. They would measure the redshift to get the speed, and then use the supernova's observed dimness to calculate the precise distance. They were building a map of the cosmos, plotting the expansion history of the universe across billions of years. They expected to see the steady, graceful slowdown of cosmic growth, the gentle tug of gravity putting the brakes on the Big Bang's initial fury. They were about to find something that would shatter that expectation entirely. The two teams racing to measure the cosmos were not expecting a revolution. The Supernova Cosmology project and the High-Z Supernova Search team were locked in a friendly but intense competition, each peering deeper into space than ever before. They had collected their precious data from ancient stellar explosions, the standard candles that would reveal the universe's past. They assumed their hard work would confirm a simple story, that the collective gravity of all the galaxies was slowly putting the brakes on cosmic expansion. The data told a different story entirely. When they finally plotted their results, the distant supernova were fainter than their models predicted. These beacons from the far reaches of time were not just far away, they were even farther than they should have been. The only possible explanation was as simple as it was terrifying. The expansion of the universe was not slowing down, it was speeding up. Picture throwing a ball straight up into the air. You expect it to slow, stop, and fall back to the ground. Now imagine watching that ball not only fail to fall back, but shoot away into the sky, moving faster and faster the farther it goes. That is precisely what the supernova data revealed the universe is doing. The initial reaction within the teams was profound disbelief. They checked and rechecked their work. They searched for errors, for some hidden flaw in their measurements or in their understanding of the supernova themselves. Could interstellar dust be dimming the light? Were the ancient supernova fundamentally different from modern ones? Every alternative was investigated and systematically ruled out. The evidence was relentless. The conclusion was inescapable. When the two rival teams announced their nearly identical findings in 1998, the scientific world was thrown into chaos. This was not a minor adjustment. It was a complete overturning of our most fundamental understanding of cosmic destiny. The discovery had to survive the gauntlet of peer review, a process of intense scrutiny by the entire cosmological community. The data was solid, the result was confirmed. The universe was being pushed apart by a mysterious, repulsive force, a presence we now call dark energy. In an instant, cosmology was forced to confront a new and bewildering reality, one where an unknown form of energy dominates the cosmos and dictates its ultimate fate. Long before those supernova observations, the seeds of this mystery were already planted by the greatest scientific mind of the 20th century. Albert Einstein was building his theory of general relativity, a revolutionary new description of gravity, and he turned his equations onto the universe itself. He believed the cosmos was eternal and static, neither expanding nor contracting. But his own math told a different story. His equations predicted that a universe filled with matter should be dynamically changing, either collapsing under its own gravitational pull or flying apart. This deeply troubled him. To force his equations into alignment with the static universe everyone believed in, he added a small, arbitrary mathematical term, a fudge factor he called the cosmological constant. This constant represented a kind of repulsive force, an anti-gravity that worked on the largest scales to perfectly balance the inward tug of gravity, propping up a stationary cosmos. Then came Edwin Hubble's monumental discovery. The universe was not static at all, it was expanding. Einstein saw the evidence and immediately realized his error. He famously discarded the cosmological constant, calling it the greatest blunder of his entire career. For decades, this mathematical ghost was forgotten, a curious footnote in the history of a brilliant mistake. The irony is breathtaking. The very thing Einstein invented to hold the universe still, and then threw away as nonsense, is precisely what modern cosmologists needed to explain why it is flying apart. That repulsive force, the cosmological constant, has been resurrected as the simplest and most direct candidate for dark energy. It is as if the universe was whispering the answer to Einstein all along, but he was not yet ready to listen. This is the beautiful, humbling nature of science. An idea deemed a failure can lie dormant for generations, only to be reborn as the key to a deeper truth. So what could this cosmic repulsion actually be? If it is Einstein's constant, it points to a bizarre property of empty space itself. So we have a name for this mysterious force, dark energy. It is the label we give to whatever is causing the cosmic acceleration, and it is not just a small component of the universe. Current measurements tell us that dark energy makes up about 68% of everything, the dominant ingredient in the entire cosmic recipe. It is crucial to distinguish it from its similarly shadowy cousin, dark matter. Dark matter is the invisible scaffolding that holds galaxies together with its gravitational pull. It acts like a cosmic glue. Dark energy, in stark contrast, is a cosmic repulsion. It does not clump or pull, it pushes, and its effect only becomes noticeable on the very largest scales, across the vast voids between galaxy clusters. Its defining characteristic is a bizarre property known as negative pressure. Think of pressure as a force that pushes outward, like the air in a balloon. But dark energy's negative pressure is different. It acts like a tension, a stretching force woven into the fabric of space itself. A simple analogy is a piece of rubber. If you stretch it and let go, it will snap back. But if that rubber had the property of dark energy, stretching it would make it want to stretch even more, accelerating its own expansion without any additional effort. This is what appears to be happening to the universe. Empty space is not nothing. It possesses this innate tension, and as the universe expands, more space is created, which in turn creates more of this repulsive force, leading to a runaway acceleration. The profound and humbling truth is that dark energy is less a solution and more a placeholder for our ignorance. We have measured its overwhelming effect. We know it dictates the fate of the cosmos, but we have no idea what it actually is. Is it Einstein's cosmological constant, a fixed energy density of the vacuum, or is it something far stranger and more dynamic, a field that changes over time? This question stands as one of the greatest unsolved mysteries in all of physics. If empty space itself has this innate tension, then what exactly is filling the void? To find an answer, we must journey into the bizarre world of quantum physics, where nothing is ever truly empty. According to quantum field theory, the vacuum of space is a seething, bubbling cauldron of activity. So-called virtual particles are constantly flickering into existence and then vanishing almost instantly. Think of it like a pot of water on the verge of boiling. Even when the surface looks perfectly still, tiny bubbles are constantly forming and collapsing, a hidden frenzy of energy just beneath the calm exterior. In the quantum vacuum, these fleeting particle pairs borrow energy from nothingness, exist for an unimaginably short moment, and then annihilate each other, returning the energy back to the void. This endless cycle of creation and destruction is not just a theoretical curiosity, it has real consequences. All this frantic activity should imbue every cubic centimeter of space with a fundamental energy, a background hum known as vacuum energy. This vacuum energy, with its repulsive gravitational effect, behaves exactly like Einstein's cosmological constant. It seems we have our culprit, a natural source for dark energy born from the fundamental laws of quantum mechanics. But here is where the story takes a sharp turn into the truly inexplicable. When physicists calculate how much energy this quantum frenzy should produce, the result is so catastrophically large it defies all reason. The math suggests a vacuum energy density so immense that it should have ripped the universe apart in the first split second of its existence. Stars, planets, and galaxies could never have formed. The calculated value is a number with 120 zeros after it. That is 10 to the power of 120. Now compare that to the incredibly tiny, gentle amount of dark energy we actually observe. The discrepancy is not just a small error, it is the largest mismatch between theory and observation in the entire history of science. We have a prediction that is off by a factor of 1 followed by 120 zeros. This colossal failure is known as the cosmological constant problem, and it stands as a glaring signpost that our deepest theories are incomplete. Our two most successful descriptions of reality, quantum mechanics and general relativity, are giving us two completely different answers for the energy of empty space. One tells us the void should be bursting with unimaginable force, while the other shows us a cosmos where its effect is subtle yet dominant. Some fundamental piece of the puzzle is missing. a key that can reconcile the furious quantum world with the serene expansion of the cosmos. This colossal mismatch forces us to consider a radical possibility. Perhaps dark energy is not a fixed property of the vacuum at all. What if it is something that can change, a dynamic force that evolves over the lifetime of the cosmos? This idea has a name, quintessence. Imagine a new kind of field, an invisible energy that permeates every corner of space, much like a magnetic field but with a repulsive push. This is the essence of quintessence, a theoretical scalar field that could be the source of the cosmic acceleration. Its behavior would not be locked in place like Einstein's constant. Instead, it could weaken or strengthen as the universe ages, its influence waxing and waning over billions of years. This concept is not entirely without precedent. Cosmologists believe a similar field, called the inflaton field, drove a period of incredibly rapid expansion in the very first moments after the Big Bang, a burst of growth known as cosmic inflation. Quintessence could be a much slower, gentler cousin of that primordial engine, a late-time echo of that initial explosive event. The implications of a dynamic dark energy are profound. If quintessence is real, then the fate of the universe is not yet sealed. The current acceleration might not be a one-way ticket to oblivion. Could this repulsive force eventually fade away, allowing gravity to regain control? Or might it grow stronger, leading to an even more violent end? A quintessence field opens the door to these startling scenarios, transforming our cosmic destiny from a foregone conclusion into an open question. The challenge, of course, is that a field you cannot see or touch is incredibly difficult to prove. How do you measure the subtle evolution of something that is everywhere and yet reveals itself only through its grandest effect on the entire universe? The search for an answer is pushing our telescopes to their absolute limits as we try to measure the expansion history with ever greater precision, looking for the faintest whisper of change in dark energy's relentless push. To distinguish between these competing ideas, from a static vacuum energy to a dynamic field, cosmologists have a powerful tool, a single number known as the equation of state parameter. Think of it as the identity card for dark energy, a code that describes its fundamental character. This parameter, labeled with the letter W, defines the precise relationship between the pressure dark energy exerts and its energy density. For the simple case of Einstein's cosmological constant, a fixed energy of empty space, this number is exactly -1. A value of W equals -1 represents a constant, unchanging force. But if dark energy is something like quintessence, a field that evolves, then W would be different. It might be greater than -1, or in an even more dramatic scenario, it could be less than -1. This is where the story takes a truly dark turn. A value of W less than -1 describes something called phantom energy. This is not just a repulsive force, it is a self-amplifying cosmic poison. The peculiar physics of phantom energy suggests its density would actually increase as the universe expands. This creates a terrifying positive feedback loop. More expansion means more phantom energy, which causes faster expansion, which creates even more phantom energy. The end result of this runaway cycle is a cosmic doomsday known as the Big Rip. In this scenario, the accelerating expansion does not just push galaxies apart. Billions of years from now, as the phantom energy grows overwhelmingly strong, it would first tear apart galaxy clusters, then individual galaxies. The relentless force would eventually rip stars from their solar systems. In the final moments, it would overcome the gravity holding planets together, then the electromagnetic forces binding atoms, and finally, it would shred the very fabric of spacetime itself. The entire universe would be torn into a thin, cold mist of fundamental particles, forever isolated and alone. This ultimate fate hinges entirely on the value of W. Measuring this single number with extreme precision has therefore become one of the most important goals in all of modern cosmology. How do we possibly measure a property of something we cannot see? Astronomers use a multi-pronged attack combining the power of different cosmic probes. They return to the distant supernova, those standard candles, to trace the expansion history with ever greater detail. They study the faint afterglow of the Big Bang, the cosmic microwave background, which holds a frozen imprint of the universe's early composition and geometry. And they map the large-scale structure of the universe using Baryon acoustic oscillations, the faint ripples in the distribution of galaxies that act as a cosmic ruler. By combining these independent lines of evidence, scientists can triangulate the value of W. Is it exactly -1, or is it something else? Every new observation, every more detailed map of the sky, brings us closer to an answer. This single parameter holds the key to our cosmic destiny, determining whether the universe will end in a slow, cold expansion or in a violent, catastrophic tear. To trace the subtle evolution of dark energy, we must listen for an echo from the very beginning of time. In its first few 100,000 years, the universe was not a transparent void but a seething, opaque ocean of primordial plasma. Light in the form of photons was trapped, constantly pushing against the soup of ordinary matter particles, the baryons. This created a cosmic tug-of-war, with gravity trying to pull matter together and the intense radiation pressure pushing it apart. This battle generated powerful sound waves that rippled outward through the young cosmos, traveling at nearly half the speed of light. Then, in a single, transformative moment, the universe cooled enough for atoms to form. The photons were suddenly set free, creating the cosmic microwave background we observe today, and the sound waves instantly froze in place. They left behind a permanent, fossilized imprint, a subtle preference for galaxies to form at a specific distance from one another. That preferred scale is the Baryon acoustic oscillation, a cosmic ruler etched into the sky. Its size is immense, roughly 500 million light-years across. This is the standard yardstick of the universe. Today, massive astronomical projects are using this ruler to measure cosmic expansion with breathtaking precision. Surveys like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument are not merely taking pictures of the sky, they are creating monumental three-dimensional maps. They painstakingly measure the positions and redshifts of millions upon millions of galaxies, building a chart of the cosmos so vast it reveals the large-scale structure of everything. Within this cosmic web of galaxies and vast voids, scientists can detect that subtle, frozen echo. They look for a statistical excess of galaxies separated by that 500 million light-year distance. This is the Baryon acoustic oscillation signal. By measuring how the apparent size of this ruler changes across different cosmic epochs, we can see how the fabric of space has been stretched over billions of years. If dark energy has been constant, the ruler will stretch in one predictable way. If it is dynamic like Quintessence, the stretching will tell a different story. This method provides a powerful and completely independent check on the results from supernova, cross-examining the universe's own expansion history using the very vibrations from its infancy. Sometimes the most profound truths are found by accident. In 1964, two radio astronomers, Arno Penzias and Robert Wilson, were troubleshooting a persistent, maddening hiss in their giant horn antenna in New Jersey. They pointed the instrument at the sky, and the noise was there day and night, coming from every direction. They scrubbed the antenna clean of pigeon droppings. They checked every connection, but the faint, uniform static refused to go away. They had no idea they were listening to the birth cry of the universe. This persistent whisper was the cosmic microwave background, the cooled and faded afterglow of the Big Bang itself. When the universe was just 380,000 years old, it cooled enough for the first atoms to form, allowing light to travel freely for the very first time. That primordial light has been traveling for over 13 billion years, stretched and cooled by the expansion of space into the faint microwave signal that Penzias and Wilson so famously stumbled upon. This cosmic backdrop is not perfectly smooth. If you could see it with microwave eyes, the entire sky would glow with a nearly uniform temperature of just 2.7 degrees above absolute zero. But embedded within that uniformity are the tiniest of fluctuations, minuscule variations in temperature, mere millionths of a degree. These imperfections are the most important fossils in all of cosmology. They are the seeds of all structure in the universe, a slightly denser patch of that ancient plasma, a tiny hotspot, held just a little more gravitational pull, eventually attracting more matter over billions of years to become a vast galaxy cluster. A cooler, less dense patch would evolve into one of the great cosmic voids. The pattern of these hot and cold spots is a frozen baby picture of the cosmos, a map of its potential. Space missions like Planck, a European Space Agency observatory, have mapped these temperature anisotropies with breathtaking precision. By analyzing the specific size and distribution of these spots, cosmologists can decode the fundamental parameters of the universe. The geometry of these spots tells us the overall shape of the cosmos. The data is unequivocal. The universe is geometrically flat. This flatness, a critical prediction of cosmic inflation, has a stunning implication. It tells us the total density of matter and energy in the universe must be exactly the critical value needed to balance its expansion. When you add up all the ordinary matter and all the dark matter we can detect, it only accounts for about 32% of that critical density. The remaining 68%, the overwhelming majority of the cosmos, must be made of something else, a smooth, uniform energy that does not clump into spots. That something is dark energy. The cosmic microwave background provides our earliest and most powerful evidence for its existence and its overwhelming dominance. It is the foundational pillar of our standard model of cosmology, a snapshot from the universe's infancy that confirms the strange reality we see today, a cosmos whose fate is ruled by a mysterious, repulsive force. The ultimate fate of our universe hinges entirely on the true nature of dark energy, depending on whether it is a constant presence, a phantom force, or a fleeting one. Cosmologists have painted three dramatic portraits of how it all might end. The first and most widely accepted scenario is the Big Freeze, also known as heat death. In this future, dark energy remains constant, and the acceleration of the universe continues at its current, steady pace. One by one, distant galaxies will be pushed beyond our cosmic horizon, their light stretched to wavelengths we can no longer detect. The sky will grow darker and emptier over trillions of years. Eventually, all star formation will cease as the raw material for new stars is locked away in isolated, aging galaxies. Those last stars will burn out, leaving behind cold, dead remnants like black holes, neutron stars, and wandering planets. Even these will not last forever. Over almost unimaginable timescales, black holes will evaporate through a process known as Hawking radiation. The universe will approach a state of absolute zero temperature, a vast, dark, and uniform sea where no energy can be extracted, no work can be done, and no new structure can ever form again. It is a quiet, cold, and eternal end, a far more violent destiny awaits us if dark energy is not constant, but a phantom energy that grows stronger. This leads to the second scenario, the Big Rip. In this timeline, the repulsive force of dark energy becomes so powerful that it overwhelms every force that holds the universe together. First, the gravitational bonds connecting galaxy clusters would snap. Then, individual galaxies would be torn asunder, their stars scattered into the ever-expanding void. As the end draws near, the phantom force would rip apart our own solar system. The gravitational grip of the sun would fail, and Earth would be flung into the darkness. In the final, terrifying moments, the force would tear stars and planets into Chinese letter. It would then overcome the nuclear forces binding atomic nuclei, and finally, it would shred the very fabric of spacetime itself. The universe would end not with a whimper, but with a catastrophic, instantaneous dissolution of all structure into a thin, lonely mist of fundamental particles. There remains a third, more cyclical possibility, the Big Crunch. This scenario requires that dark energy is not a permanent feature of the cosmos but a field that decays away over time. If the repulsive push were to fade, the ancient tug of gravity could reassert its dominion. The expansion of the universe would slow, halt, and then reverse. Galaxies would begin rushing back toward each other, their collective light blue-shifted as space itself contracts. The temperature of the cosmos would rise as everything is compressed into an increasingly smaller, hotter, and denser state. This would culminate in a fiery collapse back into a singularity, a mirror image of the Big Bang. Some theories even suggest this singularity could trigger another Big Bang, giving birth to a new universe in an endless cycle of cosmic death and rebirth. These three endings, from a silent freeze to a violent rip or a crushing reversal, are not just abstract ideas. They are the starkly different futures that depend on a single, elusive number, the equation of state of dark energy. The question of how the universe will end is therefore the very same question we are trying to answer today, a mystery written in the fading light of distant supernova and the frozen echoes of the first sound waves. Of all the possibilities, the most unsettling is a future where dark energy does not just push, but actively strengthens its own grip. This is the realm of phantom energy, a theoretical state where the equation of state parameter W falls below the value of -1. In this bizarre scenario, the density of dark energy would not remain constant or dilute as the universe grows. It would actually increase. More space created by expansion would generate even more of this repulsive force, which would then cause even faster expansion in a terrifying, self-feeding cycle. The mathematics of this runaway feedback loop suggests a shocking outcome. The expansion rate could, in theory, become infinite within a finite amount of time. The cosmos would not just expand forever, it would end on a scheduled date. The consequence of this is the most violent cosmic doomsday imaginable, the Big Rip. First, the phantom energy would overcome the gravitational glue holding clusters of galaxies together. Then, individual galaxies would be shredded, their stars scattered into the endless, accelerating void. As the final moments approached, the force would tear apart our own solar system. The sun's gravitational hold on Earth would be broken. Later, the phantom force would rip the Earth itself to pieces, then the molecules that form your body, and finally, it would overcome the nuclear forces inside every atom. In the last instant, space-time itself would be torn asunder. The universe would cease to exist as a coherent structure, dissolving into a meaningless, lonely mist of disconnected particles. This scenario pushes our understanding of physics to its absolute limit. Phantom energy appears to violate certain sacred principles in general relativity known as the energy conditions. These are rules that essentially prevent matter and energy from having exotic, negative energies that could lead to impossibilities like time travel or faster-than-light motion. Phantom energy, with its self-amplifying nature, seems to break these rules, suggesting that if it is real, our theory of gravity is incomplete or must be modified in some profound way. For now, the most precise measurements we have point to a value of W very close to -1, consistent with a simple cosmological constant. The phantom regime remains a speculative, almost ghostly possibility hovering at the edge of our data. Yet its terrifying implications ensure that astronomers will continue to chase its shadow, knowing that the ultimate fate of reality could hinge on a number just slightly less than -1. Perhaps the greatest scientific revolutions happen when we question our most fundamental assumptions. What if the problem is not with the universe but with our understanding of it? A small but determined group of physicists proposes a radical alternative. Maybe dark energy does not exist at all. Instead, our theory of gravity, Einstein's magnificent general relativity, could be incomplete. This idea suggests that cosmic acceleration is not driven by a mysterious repulsive force, but is simply a sign that gravity itself behaves differently across the vast, empty expanses between galaxies. This is not a small adjustment. It is a challenge to a cornerstone of modern physics. The theories behind this idea have names like F of R gravity, where the R stands for Ricci curvature, a measure of how space-time is warped. In simple terms, these theories propose that the strength of gravity changes depending on the environment. In the dense, crowded space within a solar system, it behaves exactly as Einstein predicted. But in the near-perfect vacuum of intergalactic space, its grip weakens in a specific way that could mimic the effects of an accelerating expansion. Think of it like this. You have a map that works perfectly for navigating your own city, but when you try to use it for the entire world, the distances seem wrong. The solution is not to invent a new, invisible force that stretches the continents. The solution is to realize your map's projection is flawed on a global scale. Modified gravity theories argue that Einstein's equations are our local map, and we need a new projection for the cosmos. The most significant hurdle for these theories is that they must pass every test that general relativity has already aced. For decades, Einstein's theory has been confirmed with stunning precision, from the precise orbit of Mercury to the way light bends around the Sun, and even in the timing of pulsars. Any new theory of gravity must reproduce all these successes within our solar system, while also explaining the cosmic acceleration that general relativity cannot account for without dark energy. This is an incredibly difficult balancing act. Furthermore, these theories must also align with the evidence from the cosmic microwave background and the large-scale structure of galaxies. It is a tall order to explain everything from the fall of an apple to the flight of a galaxy with a single, modified set of laws. The debate is far from settled, but it represents a profound philosophical fork in the road. Do we fill the universe with an invisible, dominant substance we cannot directly detect? Or do we rewrite the rules of gravity that have guided us for a century? The answer will determine not just the fate of the cosmos, but the future of physics itself. Just when we thought we had a standard model for the cosmos, a new crack has appeared in the foundation. This crack is known as the Hubble tension, and it is a discrepancy so stubborn it threatens to unravel our entire understanding of cosmic history. The Hubble constant is the number that tells us how fast the universe is expanding today. For years, we assumed we could measure this one number in different ways and get the same answer. We do not. When scientists use the cosmic microwave background, that pristine baby picture of the universe, to extrapolate forward to the present day, they get one value for the expansion rate. But when they measure it directly using modern tools like supernova and other local distance markers in our cosmic neighborhood, they get a distinctly different, faster value. The early universe method and the late universe method are giving us conflicting answers. This is not a small statistical fluke. It is a significant and persistent gap that has survived over a decade of increasingly precise measurements. It suggests that something is fundamentally wrong, either with our measurements or, more excitingly, with our standard model of cosmology itself. This model, which includes both dark matter and dark energy, might be missing a crucial ingredient. One compelling proposal is the idea of early dark energy. Imagine a third form of dark energy that was active only for a brief moment in the universe's infancy, before the cosmic microwave background was emitted. This transient burst of repulsive energy would have temporarily altered the expansion rate of the young cosmos, changing the initial conditions from which we extrapolate. It would be like a hidden push in the first act of a play that changes how we interpret the entire story. If early dark energy existed, it would mean that dark energy is not a constant, unchanging force, but something that can turn on and off or change its strength across cosmic time. This would completely reshape our understanding of what it is. The Hubble tension is more than a technical disagreement, it is a direct challenge. It forces us to ask whether we have been too complacent, whether the mysterious 68% of the universe is even more bizarre and dynamic than we ever dreamed. Resolving this crisis may require new physics that goes beyond Einstein, potentially redefining the dark energy that holds the key to our ultimate fate. These ghostly particles are streaming through you right now, in their trillions, every single second. They are called neutrinos, and they are among the most elusive and abundant subatomic particles in existence. Born in the hearts of stars and in the violent chaos of supernova, they flood the cosmos, barely interacting with anything at all. Most pass straight through the entire Earth as if it were not even there. For a long time, physicists believed these phantoms were completely massless, traveling at the speed of light. But we now know they do possess a tiny, almost negligible mass. And in the grand accounting of the cosmos, even the slightest mass, when multiplied by countless trillions, can add up to a meaningful influence. This is where their story intersects with the enigma of dark energy. The gravitational pull of all these neutrinos stretching across the universe subtly affects how cosmic structures form. They act like a cosmic substrate, a background sea that gently tugs on the clumping of matter. In the early universe, when neutrinos were moving at near light speed, their high energy prevented them from collapsing into the same gravitational wells as dark matter. This slowed down the growth of the largest structures, the vast filaments and clusters of galaxies we see today. By measuring this imprint on the cosmic web, we get another independent measurement of the universe's expansion history. The behavior of these particles is woven into the very fabric of the large-scale structure that dark energy is now relentlessly pushing apart. But could the connection be even deeper? Some speculative theories propose that neutrinos are not just passive bystanders in the dark energy story, they might be active participants. One fascinating idea suggests that neutrinos could be interacting with the proposed dark energy field, the quintessence we discussed earlier. In this model, the presence of neutrinos could somehow trigger the onset of cosmic acceleration. Imagine a cosmic seesaw. In the early, dense universe, neutrinos had high energy, and their influence kept the dark energy field in a dormant state. But as the universe expanded and cooled, the neutrinos lost energy. This shift could have acted like a switch, releasing the pent-up repulsive force of the dark energy field and initiating the accelerated expansion we see today. Another line of thought explores the possibility that the properties of neutrinos themselves, perhaps their masses, have changed over cosmic time. A subtle evolution in the neutrino sector in the late universe could, in principle, contribute to the effective behavior we attribute to dark energy. While neutrinos are almost certainly not the primary driver of cosmic acceleration, their mass and behavior represent a critical piece of the puzzle. They are a tangible link between the infinitesimally small world of particle physics and the impossibly large scale of cosmology. Every time we detect a neutrino, we are catching a whisper from a stellar furnace, a messenger that has traveled across space and time, carrying with it clues not just about the lives of stars, but about the ultimate fate of the entire cosmos. This deep entanglement shows that to solve the mystery of dark energy, we cannot only look to the heavens with our telescopes, we must also peer into the subatomic realm, seeking answers in the behavior of the universe's most ghostly inhabitants. This line of reasoning forces us to confront a deeply philosophical question. Why is the amount of dark energy so perfectly tuned for our existence? The value we observe is incredibly small, yet if it were just slightly larger, the consequences would have been catastrophic. A dark energy density only a few times greater than what we measure would have caused the universe to accelerate so rapidly in its youth that galaxies, stars, and planets could never have pulled themselves together. Gravity would have been defeated before it could build any structure at all. The cosmos would be a vast, empty, and ever faster expanding void, devoid of any complexity or life. Conversely, if dark energy were significantly weaker or even negative, the universe might have collapsed back on itself long ago in a big crunch, snuffing out any possibility of life in a fiery reversal. The window for a life-permitting universe is astonishingly narrow. This apparent fine-tuning leads us to a principle that is as profound as it is contentious, the anthropic principle. In its simplest form, it suggests that the universe must have the properties it does because we are here to observe it. The constants of nature, like the density of dark energy, are not random. They are what they are because if they were any different, we would not exist to ask the question. This shifts the entire inquiry. We stop asking why the value is so specific and instead recognize that we could only ever find ourselves in a universe where the value allows for our existence. This logic finds its most dramatic extension in the concept of the multiverse. Imagine not one universe, but a vast, perhaps infinite, ensemble of universes, each with its own unique, randomly selected set of physical laws and constants. In most of these universes, the dark energy density is too high or too low for life to ever arise. They are sterile, empty, or short-lived, but in a tiny, improbable fraction of them, the numbers just happen to line up perfectly. We, of course, find ourselves in one of those rare, life-friendly bubbles, not because of any special destiny, but simply because it is the only kind of universe we could possibly inhabit. To some, this is a compelling answer to the fine-tuning problem, a natural outcome of a much larger cosmic landscape. To others, it feels like a philosophical cop-out, an untestable retreat from finding a deeper, more fundamental reason within our own universe. This perspective does not solve the mystery of dark energy, but it radically reframes it, placing our cosmic home within a potentially limitless and wildly varied family of universes, most of which are utterly inhospitable to anything we would recognize as life. The next great leap in this cosmic detective story is already taking shape, not just in theory, but in steel, glass, and silicon. A new generation of astronomical observatories is being built with one primary goal: to finally unmask dark energy. These are not merely new telescopes, they are entire cosmic cartography, missions designed to map the history and structure of the universe with a precision that was once unimaginable. Leading this charge from space is the Nancy Grace Roman Space Telescope, named for a pioneering NASA astronomer. This observatory will perform a survey of staggering scope. It will hunt for thousands of distant Type 1 supernova, those crucial standard candles, building a timeline of cosmic expansion far more detailed than anything we have now. But Roman's power does not stop there. It will also master a subtle phenomenon known as weak gravitational lensing. This occurs when the gravity of dark matter, the invisible cosmic scaffolding, warps the fabric of space itself, distorting the light from galaxies behind it. By measuring the minute twists and stretches in the shapes of billions of galaxies, Roman will create a three-dimensional map of the dark matter distribution across the universe. This map is a direct record of how cosmic structure has grown over time, a growth rate that dark energy actively suppresses. By comparing the history of expansion from supernova with the history of structure growth from weak lensing, Roman will deliver a powerful, independent cross-check on the nature of dark energy, testing whether its repulsive strength has changed. Meanwhile, soaring through space on a parallel quest is the European Space Agency's Euclid mission. Euclid is a dark energy hunting specialist designed to chart the cosmos over an immense portion of the sky. It will map the positions and shapes of billions of galaxies, tracing the cosmic web back through 10 billion years of cosmic history. Its sharp eyes will measure two key phenomena with exquisite accuracy. The first is cosmic shear, the specific pattern of distortion from weak gravitational lensing. The second is the Baryon acoustic oscillation signal, that frozen echo from the early universe that acts as a standard ruler. By tracking how this ruler's apparent size has changed across different cosmic epochs, Euclid will provide another exquisitely precise measurement of how dark energy has shaped the universe's expansion. Back on the ground, a colossal eye will soon open to the sky, fundamentally changing the pace of discovery. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, or LSST, is an endeavor of almost unbelievable scale. Its massive mirror and giant digital camera will image the entire southern hemisphere sky not just once, but over and over again, every few nights for a decade. This will create an unprecedented cosmic movie, a time-lapse of the universe. The LSST will discover millions of supernova, far more than all previous surveys combined. It will catalog billions of galaxies for weak lensing and Baryon acoustic oscillation studies. It will watch as asteroids move, as stars vary, and as the very sky changes before our eyes. The sheer volume of data will be measured in petabytes, revealing subtle patterns and rare events that smaller surveys could never hope to capture. Together, these missions represent a unified assault on the unknown. They will collect data of such immense quantity and quality that they will either confirm our standard model of a constant dark energy with unshakable certainty, or they will finally uncover the subtle deviations that point toward a dynamic field like Quintessence, or even something more exotic. The answers are written in the sky, in the faint light of ancient explosions and the distorted shapes of distant galaxies. We have built the tools to read that story, and we are just beginning to turn the page. Einstein's theory gives us a way to see the invisible by watching how it bends light. This phenomenon, known as gravitational lensing, occurs because massive objects warp the very fabric of space-time around them. Think of space as a taut rubber sheet. Placing a heavy weight like a galaxy cluster creates a deep depression. When light from a more distant galaxy travels near this depression, its path is curved, much like a marble would roll around the edge of a bowl. This cosmic trick of light allows us to literally see the gravitational footprint of immense structures, including the dark matter that holds them together. But for every dramatic, arc-shaped Einstein ring created by a massive cluster, there are countless subtler distortions happening across the sky. This is the realm of weak gravitational lensing. Instead of creating multiple images or obvious rings, the gravity of vast, unseen clumps of dark matter imperceptibly shears the light from billions of background galaxies, stretching their shapes in a coherent, whisper-thin pattern. Each individual distortion is tiny, almost negligible, but by measuring the subtle, coherent alignment in the shapes of millions of galaxies, astronomers can statistically map the underlying distribution of all the matter, both light and dark. This intricate map of cosmic shear is a direct record of how the cosmic web has grown over billions of years, and this is where the story connects directly to dark energy. The relentless push of dark energy works against gravity's pull, suppressing the growth of these vast cosmic structures. By measuring how much the universe's structure has clumped over cosmic time, weak lensing gives us a history of the struggle between gravity and dark energy. Powerful surveys don't just take pictures of galaxies, they analyze the faint, distorted shapes of countless galaxies to measure this cosmic shear. The pattern of these distortions tells us not only where the dark matter is, but how its distribution has evolved. This provides a completely independent method to probe dark energy, one that relies purely on the geometry of space-time and the laws of gravity, rather than on the perceived brightness of standard candles like supernova. When the results from cosmic shear align with those from supernova and the cosmic microwave background, our confidence in the reality of dark energy grows exponentially. We are using the bends in light itself to weigh the influence of the universe's most mysterious component, cross-examining the cosmos with its own fundamental laws. This staggering mismatch is not just a small error, it is a screaming anomaly. The theoretical calculation for the quantum vacuum energy is a number of almost unimaginable size, around 10 to the power of 112 ergs per cubic centimeter. The dark energy density we actually observe is a whisper in comparison, a mere 10 to the power of -8. The difference between these two numbers is a factor of 1 followed by 120 zeros. To grasp the sheer scale of this failure, imagine predicting that a single raindrop would contain more water than all the oceans on Earth combined. Our best theories are not just a little wrong, they are catastrophically, bewilderingly incorrect. This is the cosmological constant problem, and for physicists, it is a profound embarrassment, a glaring sign that we are missing something fundamental about how the universe works. How can the furious energy of the quantum vacuum result in such a gentle, barely their cosmic push? Proposed solutions often involve elegant mathematical symmetries that could, in theory, cancel out almost all of this vacuum energy. One leading candidate is supersymmetry, a concept from particle physics that proposes every known particle has a hidden superpartner. In a perfectly supersymmetric universe, the positive energy contributions from particles and the negative energy contributions from their superpartners would perfectly balance, resulting in a net vacuum energy of 0. The problem is we do not live in that perfect universe. If supersymmetry exists, it must be a broken symmetry, meaning these superpartners are too heavy for our current particle colliders to detect. This breaking would spoil the perfect cancellation, but it could leave behind just the tiny, residual energy we see as dark energy. Another, more radical idea comes from string theory, which suggests our universe is just one bubble in a vast multiverse, a cosmic landscape of perhaps 10 to the 500 different possible universes, each with its own random value for the vacuum energy. In this dizzying panorama, most universes have cosmological constants so large they are instantly torn apart. We, inevitably, find ourselves in one of the incredibly rare bubbles where the number is just small enough to allow for galaxies, stars, and life to form. This landscape picture offers an explanation, but to many, it feels like a surrender, trading a fundamental physical law for a statistical fluke. The truth is, none of these proposals have been confirmed. The cosmological constant problem remains a monument to our ignorance, the clearest possible signal that merging the quantum world with the cosmic scale of gravity is the next great frontier for physics. Uniting these two pillars of modern science is the ultimate goal, and until we do, the true nature of empty space will remain one of the deepest mysteries of all. This vast cosmic landscape emerges from a leading candidate for a theory of everything, string theory. It suggests that the fundamental constants of physics are not unique or inevitable. Instead, they can be frozen into different values as the cosmos cools, much like water freezing into ice crystals with random shapes. The result is not one universe, but a multiverse, a sprawling collection of pocket universes, each with its own random set of physical laws. In this grand cosmic lottery, the strength of gravity, the mass of an electron, and crucially, the density of dark energy are all up for grabs. The vast majority of these universes would be stillborn. If the dark energy value were even slightly larger, space would have expanded with such ferocity that no galaxies could ever coalesce. If it were negative, the cosmos might have collapsed back on itself long ago. Our universe, with its peculiarly small but non-zero value, is not a miracle of fine-tuning in this view. It is simply a winner of a statistical jackpot, one of the rare, habitable bubbles in an otherwise lifeless metacosmos. The profound implication is that we should not be surprised to find ourselves in a universe that allows for our existence, because we could not possibly observe one that does not. This elegantly reframes the question from why is the number so small to what kind of universe can support life. Yet this breathtaking idea comes with a formidable challenge. How can we ever test it? If other universes are permanently separated from our own by an inflating void, forever beyond any possible observational horizon, does the multiverse hypothesis cross the line from testable science into pure metaphysics? Proponents argue that the theory can still make statistical predictions about the expected distribution of constants we should observe across the ensemble of viable universes. Finding that our measured value of dark energy sits in a statistically likely spot within that predicted distribution could be considered indirect evidence. For now, the multiverse remains one of the most speculative, yet also one of the most serious, attempts to grapple with the deepest fine-tuning problem we have ever encountered. It pushes the very definition of science to its limit, forcing us to ask whether the ultimate explanation for our reality lies not within our own cosmic horizon, but in the unimaginable diversity that may lie beyond it. The universe seems to have a deep affinity for acceleration. Its very first moments were defined by a burst of expansion so violent it makes today's dark energy seem placid by comparison. This was cosmic inflation, a brief but spectacular epoch when the universe ballooned from smaller than a proton to a macroscopic size in a fraction of a second. The engine behind this explosive birth was a hypothetical field called the inflaton, which filled space with a repulsive gravity, pushing everything apart at a speed far exceeding that of light. Then, just as suddenly, this field decayed, its energy transforming into the hot soup of particles that would become our universe. For billions of years, the cosmos expanded at a more sedate pace until dark energy took over and reignited the acceleration. So are these two events connected? Could the dark energy we see today be a faint echo of that primordial force, a dormant inflaton field stirring back to life on a cosmic timescale? The parallels are tantalizing. Both phenomena are driven by a form of energy that generates a repulsive gravitational push, causing space itself to stretch at an accelerating rate. The critical difference lies in their intensity and duration. Inflation was an unimaginably powerful, short-lived sprint, while dark energy is a gentle, persistent marathon. One theory suggests that quintessence, the dynamic form of dark energy, could indeed be a distant cousin of the inflaton, perhaps the same fundamental field that powered the Big Bang's explosive start has been lying dormant, its energy diluted by the universe's expansion, only to re-emerge in this new, weaker form to guide the cosmos's late-time evolution. This idea offers a beautifully unified vision, linking the universe's birth to its ultimate fate under a single physical principle. If true, it would mean that acceleration is not a random anomaly but a fundamental feature woven into the fabric of space-time, a cosmic rhythm of speeding up that defines existence from its first instant to its final breath. Unraveling this connection is more than an academic exercise. It is a quest to see if the entire story of the cosmos, from its fiery beginning to its cold end, is written in a single, coherent language. This cosmic battle between attraction and repulsion is written across the sky in a structure of breathtaking scale. The universe is not a random scatter of galaxies. It is a vast cosmic web, an intricate architecture of glittering filaments, dense clusters, and immense empty voids. This is the largest pattern in existence, and its form is the direct result of a tug-of-war that has raged for billions of years. On one side is gravity, the relentless force that pulls matter together. It works to build structure, drawing gas and dark matter into dense knots where galaxies form, and then gathering those galaxies into massive clusters. On the other side is dark energy, the mysterious repulsive force that works against gravity's pull. It does not destroy the web, but it fundamentally changes its growth and ultimate shape. Think of the cosmic web as a growing city. Gravity is the construction crew, constantly building new skyscrapers and connecting them with bridges and roads. Dark energy is like a force that stretches the land the city is built on, making it harder and harder for the construction crews to reach each other and add new floors to the buildings. The city still exists, but its future growth is stifled. Supercomputer simulations of the universe show this dynamic with stunning clarity. When scientists run models without dark energy, gravity continues to pull matter into the filaments and clusters unabated. The cosmic web grows ever denser and more intricate over time, but when they add dark energy into the equations, the simulation changes dramatically. The growth of these massive structures slows. The vast voids between the filaments, already empty, begin to expand at a faster rate. Dark energy acts as a cosmic tension, stretching the empty regions more efficiently than the dense ones, effectively isolating the clusters and filaments from one another. This is why the cosmic web we see today has a specific, frozen-in-time appearance. Its grand filaments and great walls of galaxies represent the high watermark of gravity's constructive power, a moment before dark energy's push began to dominate. The delicate balance between these two forces has carved the channels through which galaxies flow and has determined the empty deserts that stretch between them. Every thread of this cosmic spiderweb and every immense void it surrounds is a permanent record of this fundamental conflict, a snapshot of the universe at the precise moment its expansion began to accelerate. The ultimate fate of the cosmos rests on a single, deceptively simple question. Is the push of dark energy a permanent fixture of the universe, or is it a force that fades or grows with time? We have a name for the first possibility: Einstein's cosmological constant, a steady, unchanging energy woven into the fabric of space itself. In this future, the acceleration we see today continues at its current, relentless pace, leading inevitably toward that cold, dark expansion known as the Big Freeze. The alternative is far more dynamic and uncertain, a form of dark energy called quintessence, a field that could be slowly weakening or, more alarmingly, growing stronger. If quintessence is real, then the universe's destiny is not yet written in stone. The current acceleration could be a temporary phase, one that might reverse or evolve into something even more extreme. To solve this, astronomers need to do more than just measure the universe's current expansion rate. They need to watch that rate change over billions of years. They need to see the cosmos speed up in real time. This sounds impossible, but there is a way to witness this cosmic acceleration directly, a method known as redshift drift. Think of the light from a distant galaxy as a unique cosmic fingerprint. Its spectral lines shifted toward the red by the expansion of the universe. If dark energy is a true constant, that redshift will remain locked in place for all eternity. But if dark energy is dynamic, that fingerprint will subtly change over time. As the universe's expansion accelerates, the stretching of space will itself get faster. This means that the light from that distant galaxy will become even redder over millions of years. We are not talking about a change you could see in a human lifetime, or even over 1,000 years. We are looking for a shift so incredibly slow and subtle that it pushes the limits of our detection. Future observatories, like the colossal, extremely large telescope being built in Chile, are being designed with this very goal in mind. With a mirror spanning 39 meters, this behemoth will collect enough light to stare at the same ancient quasars for years, even decades, searching for that minute change in their redshift. It is a patient, painstaking experiment on a cosmic scale, a direct test of whether the universe's engine of acceleration is set to a fixed throttle or if it possesses a variable control. The answer will tell us if we are living in a universe destined for a long, quiet fade, or one headed for a more dramatic and unpredictable conclusion. Dark energy presents not one, but a cascade of theoretical nightmares for physicists. The first is its inexplicably tiny value. The amount of repulsive energy we measure in empty space is minuscule, a whisper of a force. Yet, according to our best quantum theories, the vacuum should be roaring with an energy trillions upon trillions of times stronger. This is not a small rounding error. It is the largest discrepancy between prediction and observation in the entire history of science. Fitting dark energy into the established framework of particle physics is like trying to fit an elephant into a shoebox. The structure simply cannot contain it. There is no known particle or field within the Standard Model, the grand catalogue of all fundamental particles, that can account for this gentle, pervasive push. Its very nature defies the ingredients we have to work with. Then there is the bizarre property of negative pressure. We are accustomed to pressure being a pushing force, like air inflating a balloon. Dark energy behaves like a tension, a stretching force inherent to space itself. This negative pressure is what generates the repulsive gravity that drives the acceleration, a concept that feels alien even within the weirdness of general relativity. Perhaps the most philosophically unsettling puzzle is the coincidence problem. Dark energy's density and the density of matter in the universe are now roughly comparable, but this is a fleeting moment in cosmic time. For billions of years, matter was completely dominant. Only in the recent cosmic past, around the time our solar system was forming, did dark energy begin to take over. Why now? Why did this cosmic transition happen at the precise epoch when intelligent life finally evolved to notice it? It feels like a strange cosmic alignment, as if the universe became aware of its own observers. These are not minor puzzles, they are fundamental cracks in the foundation of modern physics. They scream that our understanding of reality is incomplete. Solving the dark energy enigma will likely require a revolution. a new theory that seamlessly merges the cosmic gravity of Einstein with the frantic quantum world, a framework that can finally explain why empty space is not empty at all, but filled with a mysterious force dictating the fate of everything. Even the most elegant model of the cosmos can develop hairline fractures under the intense gaze of new data. Beyond the stubborn puzzle of the Hubble tension, other observational ghosts are appearing in the machine, subtle quirks that challenge the clean narrative of our standard cosmological model. One of the most perplexing is a feature known as the CMB cold spot. In the otherwise remarkably uniform afterglow of the Big Bang, there exists a region of sky that is significantly colder than its surroundings. This is not just a minor statistical fluctuation. It is a vast, frigid patch so large and so cold that it stands out as a genuine anomaly. The simplest explanation would be that it is a giant cosmic void, an immense emptiness in space where there are fewer galaxies and thus less gravitational energy to subtly heat the passing CMB light. Yet when astronomers search for such a void in that direction, they find nothing large enough to account for the profound cold we observe. This leaves a disturbing possibility that the cold spot is not a structure at all, but a signature of something more exotic, perhaps a collision with another universe in the multiverse, or a flaw in our understanding of the physics of inflation itself. Then there are the mysterious large-scale flows. According to the standard model, the expansion of the universe should be the dominant motion on the largest scales, with galaxies drifting apart on the Hubble flow like leaves on a receding river. But observations reveal something else is happening. Huge swaths of the cosmos, entire superclusters containing thousands of galaxies, appear to be drifting in a coherent stream, moving en masse against the backdrop of cosmic expansion, as if pulled by a gravitational force we cannot see. This is not random motion. It is a directed river of galaxies on a scale of billions of light years. What immense source of gravity could be tugging on so much of the universe? Some theorists suggest it could be the pull from a concentration of matter so vast it lies beyond our observable horizon, a shadowy attractor whose existence would force us to rethink the very scale and structure of reality. While none of these anomalies are yet conclusive proof that our model is broken, their collective presence is a powerful siren call. In science, it is often the tiny, unexplained details, the data points that refuse to fit neatly on the graph, that ultimately lead to the greatest revolutions. The cold spot and the cosmic flows are the modern equivalents of those faint, too distant supernovae that first hinted at acceleration. They are the whispers from the edge of our understanding, urging us to look deeper and question our most fundamental assumptions about the cosmos and the dark energy that rules it. We are living in a cosmos that has written its own end, a story of accelerating expansion that leads to a cold, dark, and empty eternity. This is not a future of fiery collapse or dramatic rebirth, but a slow, silent fading of all light and life. So what meaning can our brief, brilliant lives possibly hold against such an immense and indifferent backdrop? The philosophical weight of this discovery is staggering. It forces us to confront the idea that our universe may not be cyclical or purposeful, but a one-way journey toward dissolution. In a cosmos destined for the big freeze, all our achievements, our art, our civilizations, and our memories would ultimately be erased without a trace, lost to an infinite void. This could be seen as the ultimate nihilism, a universe without a final act or a lasting audience. Yet there is another way to see it. The fact that we are here at all, that conscious beings have emerged on a tiny rock orbiting an average star, capable of not only perceiving this grand cosmic drama but of understanding its plot, is nothing short of miraculous. We are the universe becoming aware of itself. Our quest for meaning is not invalidated by a cold end. It is thrown into sharp, precious relief. The knowledge that everything is temporary does not rob our moments of significance, it makes them infinitely more valuable. This cosmic perspective is a profound lesson in humility. We are not the center of the universe, we are fleeting witnesses to its majestic and terrifying evolution. We are governed by forces, dark energy and dark matter, that we cannot see or touch, forces that operate on scales so vast they defy human intuition. This humbling realization is not a cause for despair, but a catalyst for a deeper kind of curiosity. It drives us to look up at the night sky with a sense of shared wonder, to ask the biggest questions, and to push the boundaries of knowledge simply because we must. Our search for dark energy's true nature is more than a scientific endeavor. It is a fundamental human impulse to find our place in the story. Whether the universe ends in a freeze, a rip, or a crunch, the fact that we are here to ponder its fate is a beautiful, transient spark of meaning in the vast, accelerating dark. This mysterious force has even escaped the confines of scientific journals to fuel our wildest stories. You can find dark energy, or its fictional stand-in, powering starships and threatening civilizations in blockbuster films and best-selling video games. A prime example is the Mass Effect series, where a substance called Element Zero can manipulate a mysterious energy field to create gravity-defying mass effect fields. This is a brilliant narrative twist, but it turns the real science on its head. Real dark energy does not let us build faster than light drives or personal shields. It is a smooth, background force pushing the entire cosmos apart. In other stories, this cosmic repulsion becomes a weapon of ultimate destruction, a force that villains might harness to tear apart planets. These creative liberties are not failures. They are a testament to the profound mystery dark energy represents. When science cannot provide a concrete answer, imagination rushes in to fill the void. This creates a powerful opportunity. Every time a player uses a mass relay or a movie hero confronts a dark energy threat, it opens a door. We can step through that door to explain what dark energy really is, separating the thrilling fiction from the even more astonishing truth. The real enigma is not a weapon we can wield, but a fundamental property of reality that governs the fate of every galaxy, star, and planet. By using these cultural touchpoints as a starting point, we can transform public curiosity into genuine understanding, inviting everyone to ponder the same cosmic questions that keep astronomers awake at night. The quest to understand this cosmic force has yielded more than just theories. It has given us powerful new tools here on Earth. The search for dark energy demands technology that can capture the faintest whispers of light from the edge of time, and that need for extreme sensitivity has sparked a revolution in digital imaging. To map billions of galaxies, astronomers required charge-coupled devices, or CCD, of unprecedented quality. These are the digital eyes of our largest telescopes, and the drive to make them more sensitive with less electronic noise has directly benefited fields like medical imaging. The same core technology that detects a distant supernova is now used in advanced X-ray machines and mammography systems, allowing doctors to see finer details with lower doses of radiation, leading to earlier and more accurate diagnoses. This is not a coincidence. It is a direct technological transfer from the frontiers of cosmology to the heart of modern medicine. Beyond the hardware, the sheer scale of a dark energy survey presents a monumental data challenge. A single project like the Legacy Survey of Space and Time will generate hundreds of petabytes of raw data, a volume that would be impossible for humans to sift through. To find patterns in this cosmic deluge, scientists have pioneered sophisticated machine learning algorithms and data processing techniques. These are not just for finding galaxies, They are powerful new methods for managing and extracting meaning from immense, complex datasets. These same algorithms are now being adapted to tackle big data problems in finance, weather prediction, and even traffic management, helping us find order in the chaos of modern life. Perhaps the most profound spin-off is not technological but human. Massive projects like the Euclid Space Telescope or the Dark Energy Survey are not the work of a single nation. They are grand international collaborations, uniting scientists and engineers from across the globe in a shared, peaceful endeavor. This cooperation builds bridges, shares knowledge, and inspires a new generation of students to pursue careers in science, technology, engineering, and mathematics. While we may not yet know what dark energy is, the pursuit of that knowledge has already gifted us with better medical tools, smarter data analysis, and a more connected and inspired global community. The value of fundamental research often lies not in the immediate answer, but in the beautiful, unexpected paths we are forced to create on the journey. Yet this grand quest for cosmic understanding inevitably raises a profound ethical question. Should we, as a species, dedicate billions of dollars and the focus of our brightest minds to decipher the ultimate fate of the universe, when our own world faces so many immediate and urgent challenges? It is a valid and necessary concern. With poverty, disease, and climate change demanding solutions, the pursuit of something as abstract as dark energy can seem like a luxury we cannot afford. This perspective frames fundamental research as a distant indulgence, separate from the gritty realities of human need. But this view overlooks a crucial historical truth. The drive to answer profound questions about our cosmos has consistently been a powerful engine for practical innovation right here on Earth. The very technology you are using to watch this, the internet, has roots in the need for scientists to share data about particle physics. Medical MRI machines rely on principles developed for fundamental research in nuclear magnetic resonance. The quest to map the cosmic microwave background pushed the limits of sensitive radio receivers, technology that later improved global communication systems. When we strive to see the edges of the universe, we are forced to invent new ways of seeing, and those new ways of seeing often find life-saving applications we never could have predicted. This is not a coincidence, it is a pattern. Blue sky research, the kind undertaken purely out of curiosity, expands the boundaries of the possible. It creates a high tide of technological capability that lifts all boats, solving problems we did not even know we had with tools we had to invent to peer into the darkness. Beyond the promise of future technology, this pursuit speaks to something deeply human. Our curiosity is not a frivolous trait, it is a fundamental part of our identity. We are the only species we know of that looks at the stars and asks not just where we are, but why we are here and how it will all end. To ignore these questions is to deny a part of our own nature. The search for cosmic knowledge is more than a scientific project. It is a modern form of a very ancient human practice, storytelling. For millennia, we have gathered around fires to share stories of creation and destiny. Today, we gather around the data from telescopes to continue that very same tradition, crafting a shared narrative of our cosmic home. This grand story, one that includes dark energy and the fate of galaxies, has the power to unite humanity across all borders and cultures under a single, awe-inspiring sky. It reminds us that we are all passengers on the same pale blue dot, tasked with the collective, humbling, and magnificent endeavor of understanding our place in the vast, accelerating expanse. Our descendants may one day look back on our current telescopes as primitive, blurry-eyed prototypes. The true cosmic archaeologists of the future will wield instruments of unimaginable power, designed to dig into epochs of time we can only theorize about today. They will push beyond the James Webb Space Telescope, launching observatories that can directly witness the cosmic dark ages, that mysterious era after the Big Bang's glow faded but before the first stars ignited. This was a universe shrouded in pure hydrogen and helium, a blank canvas waiting for its first brushstrokes of light. It is here, in this primordial fog, that the faintest imprints of early dark energy might be preserved. By mapping the distribution of this neutral hydrogen with incredible precision, future astronomers could see how the very first tendrils of cosmic structure were either encouraged or suppressed by this mysterious repulsive force. Did dark energy give the infant universe a subtle push, shaping the way galaxies would later form? The answer is written in that ancient darkness, waiting for a telescope powerful enough to read it. Another revolutionary tool on the horizon is the space-based Gravitational Wave Observatory. While we have detected ripples from black hole mergers, these future interferometers would hunt for waves from the universe's very first instant. They would listen for the faint echo of cosmic inflation, that initial, violent burst of expansion. Detecting these primordial gravitational waves would be like finding the fossilized vibrations of creation itself. Their pattern would reveal the energy scales of that epoch, potentially showing a direct link between the inflattened field that birthed the universe and the dark energy that governs its old age. Is dark energy simply a late-life echo of that first cosmic shout? This grand endeavor stretches far beyond a single lifetime. Unraveling the dark energy enigma is a multi-generational quest, a relay race of curiosity where one generation builds the tools and the next uses them to ask even deeper questions. It demands a sustained commitment to fundamental science, a patience that spans decades, and a belief that understanding our place in the cosmos is a goal worthy of our greatest collective effort. The final answers may not come for 100 years, but every observation we make today lays a single stone in the foundation of that future cathedral of knowledge. Two opposing forces, one pulling and one pushing, are locked in a cosmic struggle for control of the universe. On one side is dark matter, the invisible cosmic scaffolding. Its powerful gravitational pull draws matter together, building the great walls and filaments of the cosmic web. It is the ultimate architect of structure. On the other side is dark energy, the smooth, repulsive force that permeates the void. It works to push space apart, stretching the cosmic tapestry and suppressing the growth of new structures. They are the yin and yang of the cosmos, one gathering, the other dispersing. Their influence is not fixed in time. In the early universe, everything was much closer together. The density of matter was incredibly high, and gravity ruled supreme. Dark matter's pull was dominant, gathering clouds of gas into the first protogalaxies and building the foundations for everything we see today. Without this initial clumping force, the universe would have remained a formless, expanding cloud, and we would not exist. But as the cosmos expanded, the density of matter began to dilute. The particles of dark matter spread farther and farther apart, weakening their collective gravitational grip. Meanwhile, dark energy is thought to have a constant density. Think of dark matter as a finite number of seeds scattered in an expanding field. As the field grows, the seeds become more sparse. Dark energy, however, is like a property of the field itself. As the field gets larger, the total amount of this repulsive energy increases. There was a cosmic tipping point, roughly 5 billion years ago, when the universe had expanded enough for the steady push of dark energy to finally overcome the fading pull of dark matter. This was the moment the universe's expansion began to accelerate, a transition that defines our current cosmic era. This delicate balance leads to a tantalizing question. Could these two dark titans be talking to each other? Some physicists propose they are not independent, but two sides of the same coin, interacting in a way that transfers energy between them. In these theories, dark energy could be slowly draining the strength from dark matter, or perhaps dark matter is decaying into dark energy. This interaction could explain why their energy densities are comparable today, solving the cosmic coincidence problem. If they are linked, it would mean the fate of the cosmos is governed by a single, unified dark sector, a relationship we are only beginning to probe. Unlocking this cosmic duality is the final step toward a complete story of our universe, from its first gathered structures to its ultimate, accelerating fate. To understand the cosmos, we must first build it from scratch. Inside the world's most powerful supercomputers, cosmologists are doing exactly that. They create entire virtual universes, born from lines of code and governed by the laws of physics. These are n-body simulations, digital realms where billions of particles represent clumps of dark matter, each one a seed for a future galaxy. Gravity pulls these particles together, weaving them into a cosmic web of filaments and voids, while dark energy pushes them apart in a relentless tug-of-war. The goal is breathtakingly ambitious: to rewind the tape of cosmic history and then play it forward, watching 14 billion years of evolution unfold in a matter of weeks. By altering the fundamental rules of these digital realms, scientists can perform experiments that are impossible in the real world. What happens if dark energy is a phantom force that grows stronger over time? They input a value for the equation of state parameter that is less than -1 and then run the simulation. The result is a virtual apocalypse, a big rip that tears the digital cosmos apart before its time. What if dark energy is a dynamic field called Quintessence that slowly fades away? They run the simulation again and watch as gravity eventually regains control, leading to a dramatic reversal and a big crunch. Each simulation is a unique test of a possible reality, a what-if scenario played out on a cosmic scale. The true power of these virtual laboratories lies in comparing their output to our actual universe. Researchers meticulously analyze the large-scale structure generated in the simulation, measuring how galaxies cluster and how vast the voids between them become. They then compare this digital map to the real one painstakingly charted by telescopes like the Dark Energy Survey and the future Euclid mission. They also generate synthetic weak lensing data, calculating how the gravity in their virtual universe would distort the light from billions of background galaxies. Does the pattern of distortion match the subtle shearing we observe in the real night sky? When a particular simulation with a specific set of dark energy properties produces a virtual cosmos that looks statistically identical to our own, it is a major breakthrough. It means that the theory behind that simulation is a viable candidate for reality. These digital universes have become our most powerful guides, allowing us to test the fate of the cosmos from within a computer lab, narrowing down the infinite possibilities to a handful of potential truths. You do not need a PhD to help unmask dark energy. In your own home, with just a laptop and an internet connection, you can become a cosmic cartographer. Projects like Galaxy Zoo have flung open the doors of professional astronomy, inviting hundreds of thousands of volunteers to do what computers still struggle with: visually classifying the shapes of distant galaxies. Every spiral or elliptical you identify from the torrent of telescope images is a single data point in a map so vast it helps scientists understand how the cosmic web formed and evolves under the influence of dark energy. This is citizen science, a powerful movement that democratizes discovery. It transforms the search for answers from an elite endeavor into a collective human project, where a teacher in Brazil, a retiree in Japan, and a student in Norway can all contribute to the same grand cosmological quest. This public engagement does more than just process data. It ignites a spark of wonder. When a person connects with the raw image of a galaxy 10 billion light-years away, they are no longer a passive observer, they are an active participant in the story. That moment of personal discovery can be transformative, inspiring a young person to pursue a career in science or convincing a taxpayer of the profound value in funding fundamental research. This collaborative spirit builds a global community, united not by nationality or creed, but by a shared curiosity about our universe. It proves that the greatest mysteries are not for a select few to solve in isolation, but are a challenge for all of humanity to undertake together. Our tools and intellect have limits, and this cosmic mystery may be pressing right up against them. The brain you are using to ponder dark energy evolved to spot predators on the savannah and predict the path of a thrown rock, not to intuitively grasp a force that acts on the scale of the entire cosmos. We are like goldfish in a pond, our reality defined by the familiar boundaries of our bowl. We can observe the giant, shadowy shapes moving outside, the occasional vibrations and shifting lights, but we lack the cognitive framework to comprehend the world of the human who feeds us. Our entire existence is a subset of a much larger, more complex reality we can only dimly perceive. Dark energy may be the first clear sign that we are bumping into the edge of our conceptual pond. Perhaps the mathematics needed to describe it do not yet exist, just as the bizarre rules of quantum mechanics were utterly unimaginable before the 20th century. Before then, the deterministic clockwork universe of Newtonian physics seemed complete. No one could have conceived of a reality where particles are in multiple places at once or are fundamentally unpredictable. That revolution required a complete overhaul of our intuition. Dark energy may demand an even more profound shift, a new language of physics that we have not yet invented. This is not a cause for despair, but a humbling and thrilling call to action. Every great mystery in the history of science has seemed insurmountable until the moment it was not. The key is to remain open, to question our most cherished assumptions, and to accept that the final answer might be stranger than anything we can currently dream. The universe does not owe us an explanation that fits neatly within the limits of our current understanding. Our task is to push those limits until the cosmos reveals its next great secret. From the first startling glimpse of receding galaxies to the haunting whisper of the cosmic microwave background, this journey has revealed a universe in flight. We stand now at the edge of a vast unknown, our map of reality incomplete. Dark energy is the final, formidable frontier, a mystery that has resisted every attempt at a simple explanation. It is the place where our hard-won knowledge dissolves into profound questions, pushing not only the limits of science but the very boundaries of human imagination. This puzzle forces us to confront the fundamental laws of physics, to question the nature of empty space, and to wonder about our own place in a cosmos that is not merely expanding, but accelerating away from itself. The ultimate answer may lie in a cosmological constant, a simple yet baffling feature of the vacuum. It might be a dynamic field, a quintessence that ebbs and flows across eons. Or perhaps it is a cosmic signpost, pointing toward a deeper truth that our current theories of gravity are fundamentally incomplete. Each possibility leads to a radically different future for reality itself, from an eternal freeze to a catastrophic rip. Solving this enigma will not just add a new chapter to a textbook, it will redefine our entire understanding of existence, from the quantum realm to the cosmic horizon. We are living through one of the greatest adventures of the human spirit, a collective quest to read the final pages of the universe's story. We are the universe awakening to its own astonishing and mysterious nature. The next great discovery could be yours to witness. Share your own thoughts on this cosmic riddle in the comments below, and join us as we continue our journey into the deepest unknown.